All right. So coming to the topic of the day, so we can use std function pretty dynamically. It can work with function pointers and lambdas and whatnot, callable objects. How really does it work? And such a easy and handy construct. So that's what Sarthak is here to tell us about. And not just that, I think he's going to cover shared pointer and std any also, I guess, right? So that'll be very exciting. Sarthak is a low latency C++ engineer. He joins us from Chicago, actually. He's working with a high frequency trading firm, and so his interests lie in the intersection of finance and technology, very much, and the wide applications of C++ in that domain. Pretty exciting. He has the credentials. Let's hear from Sarthak on type erasure. Sarthak, please, you can share your
Yeah,
screen.
thanks so much for the intro, Ankur. Yeah, let me just share my screen and get started. Sorry for scaring you all. I did mean 12 p.m., not 12:30 in my time zone. It's not gonna take me. I'm not gonna take 1.5 hours of everyone. Um, yeah. So as Ankur mentioned, I'm gonna be talking about type erasure today. And I want to type erasure is a very fundamental technique in C++, uh, and a lot of containers in C++, examples stored function, shared pointer, stored any use type erasure under the hood. So what I want to do is talk about these and build to type erasure from there, what type erasure exactly is. Um, Bit intro about me. I would mention I'm a C++ software engineer based in Chicago right now. I'm originally from Delhi. This is my first talk in CPP India and first talk of 2025. So I'm quite excited and hope you are as well. Um, so let's just dive right into it. Let's look at stood function to start off with. Um, so what does what's the signature of a stood function look like? So as per CPP reference, the class template stood function is a general purpose polymorphic function wrapper. You can see that in the signature, it has a template type name parameter R, which is the return type, and a variadic template pack, the bunch of the types of the arguments that the function takes in. The interesting part in the definition uh, is the phrase general purpose polymorphic. What exactly does that mean? And let's see some examples of stood function, and we'll, we'll try to identify what this polymorphic behavior in stood function is. Um, so here I have a stood function which has a return type void and takes in an integer parameter. And I'm calling that like I'm defining f display. I'm calling the variable f display the stood function, and I'm able to assign a free function which has the same signature. So my free function printnum takes in an integer as a parameter, and the return type is void. Um, so we can establish that okay, a stood function matching the same signature as a free function, um, like a stood function can be created from a free function with the same signature. Sounds good. Um, let's look at lambda expressions now. So here I have stood function with the same signature again. Return type is void, takes in an integer, and I'm able to assign it a lambda expression with the same signature. So we're able to assign a free function, a lambda expression, and in this slide I've got a function object, which is it's a structure called printnum. It implements the operator braces, takes an integer, returns void again, and I'm able to assign function objects, or commonly known as functors, to a stood function as well. So the interesting thing in the last three examples is that the type of on the right hand side that these are completely unrelated types, like it was a functor, a free function, or a lambda expression. Whereas on the left hand side, these are being assigned to the exact same type stood function with a return type void and a template and a parameter int. So that is how that is why stood function is a general purpose polymorphic container. But now this arises $1 million question. In a language like C++, which is a strongly typed language, how are we able to assign like three completely unrelated types into one common type? And this is what we are going to be like talking about today with respect to state function, and then build up on type erasure and different containers from there. So just to rephrase, this is the question that we're going to try to answer. How are we able to assign completely unrelated types to a common type stored function void of int? So let's take a step back and come up with requirements for such a container. Like if you were to build a stored function, what would be the requirements of such a container be like? So the top requirement that I've been talking about is being generic. That is the ability to hold different types sharing a common interface. The common interface that is being shared among these different types is that they all implement the operator braces, like the function call operator, take in an integer and return void. And the other requirement of such a container would be retaining the type information of the assigned objects. That is, it is type safe. Just trust me on this right now. I'll come back to type safety. But let's talk about the generic requirement for now. And for a second, if you ignore the type safety and just focus on holding different types sharing a common interface, a very common like design pattern already implements this. If you think of interfaces or abstract classes and base classes deriving from those abstract classes, they already implement the generic behavior. Let's have a look. So in this slide, I've got an interface iFunction, which has a virtual method, which has a pure virtual method. It returns a Boolean, takes in an integer, and it implements the function call operator. And then I have two different base classes which derive this from this interface, called isEvenFunctor or isOddFunctor, and they implement the operator overload. So if you look at this, it already implements the requirements. That is, it can hold different types sharing a common interface. For example, if I have a filter range function that inputs a range and a reference to this interface, I can pass either of these functors. Like I can pass isEvenFunctor, in which this filter range function would filter all the even numbers. And if I pass the isOddFunctor, it's gonna filter all the odd numbers. So it seems like this implementation already is generic and type safe as well. Interfaces by their very nature are type safe. There can be a virtual destructor, so the correct type is going to be destructed. So it seems like interfaces satisfy our requirements, but we're still falling a bit short. Interfaces have a very big shortcoming that if you have, for example, an external library function that implements the exact same signature, that is, it takes an integer and returns you a Boolean, an external library function cannot be bound to your interface. You cannot have an external library structure inherit from iFunction and then use it in this filter range method. So stood functions actually do something much smarter. In stood function, all that is required is that as long as you have an interface that takes an integer, returns a Boolean, no matter whether it implements iFunction, you can simply use it. So although this definition does seem to satisfy the requirements I just listed, it does have a very big shortcoming that it is bound only to your code. You cannot use external functions and a lot of other things. For example, like filter range expects a reference to iFunction. So you cannot simply pass a lambda in here. So it seems like the requirements that were just listed, I lied to you a bit. Those are not the exact requirements. So let's revisit the requirements and define them again. So instead of holding just different types, the actual requirement of a container like stood function would be to hold completely unrelated or related types sharing a common interface. So the unrelated part is the important part because now they cannot be bound by a common, like for example, with an inheritance hierarchy with a common interface. So let's try to come up with such a container that can be constructed. I think a smaller problem to solve is that okay, we know that this container can be assigned completely unrelated types. So a smaller problem to solve would be, how can a container be constructed from completely unrelated types? And once we know that, okay, I have this container which can be constructed from unrelated types, how do I store how do I store the values in my container and expose those to the user to be expose, for example, the operator braces to the user to be able to call it as a function. Yeah, so let's start off by building a container that can store different types, store completely unrelated types. So I'll call it a magic function container. So this magic function container should be able to hold all function-like objects implementing the signature void operator braces int. So this function should be able to be constructed from anything that implements the function call operator, takes an integer, and returns void. So at the end of this, I should be able to assign a free function print num, a lambda, or a functor to it. Okay. So step one in building such a container would be having a templated constructor. So notice that this container itself is not really templated because we do want unrelated types to be assignable to a single common type. So the magic function container is going to be that generic type, but its constructor is templated. So now that we have a templated constructor and we have a void operator which takes an int and passes that integer into the value we are storing inside the container and simply calling the value. We've solved a part of the problem. So this container is constructible from any function-like object, and we can use C++20 constraints to constrain the type name func here. I'll show it in a later slide that this func can be constrained to make sure that it is callable from an integer and it returns a void. So we've solved the problem that this can be constructed using different types. But now the tricky part remains that how do we store mval? So I've got this question mval, and that's the tricky part. What should be the type of mval? Because now the structure itself is not templated, but the constructor is templated. So how do we store this value type? We don't have the type information right now. We don't have the type information available in the class itself. It's just available in the constructor. So how do we store different types in this magic function container? I've touched upon something very similar before using interfaces. Imagine a base class interface. Let's call it concept. Imagine a base class which implements this operator, takes an integer, returns void, and it's a virtual method. But the derived class is actually templated. So I think it's easier to just look at the code. So let's try to solve the challenge of how we are going to store this value. Okay, we've got a container that can be constructed using any value. Now somehow we want a generic way to store that value. So what we can do is that we can have a base class which implements the void operator, takes an integer, returns void. But the base class is not going to be templated, but the derived class can be templated, taking a type T and inheriting from the base class. It's storing the value with a concrete type T at the very bottom of the code, implementing the operator and calling the actual, passing the integer to the actual value. So this type T, you can imagine, would be my function type. And the model is constructed from the function type. The interesting part about this is that now any type T implementing the operator braces, the function call operator with an integer, can be stored into model T. And model T itself is inheriting from a generic type concept. So imagine that I can have a concept pointer pointing to different different models created from different functions as long as they implement this operator. And that's the beauty of it. So in the previous code, I mentioned that, oh, the challenge is that how do we store this mval? What we can do now is that we can have a pointer to the concept. So this class is going to simply have a pointer to the concept, which is a base class. And we are making use of inheritance here. And this pointer to the concept can actually store different concrete types of model T, where T is going to be the function type, like of model func. And these concrete object types, because they all inherit from a generic concept type, can be stored into that pointer. So let's have a look at how that's going to look like. So on the right, I've got my magic function container. It takes in any type func and creates. You can see at the bottom that the function in the class itself is stored as a pointer to the concept, initially assigned to null pointer. On construction, what it does is that it creates a new model, taking the type function as the template type name argument, template type name parameter, and passes the actual func to it. On the left side, you can see that the model simply expects that, okay, the model can be constructed from any type T as long as the type T implements my interface, like takes in an integer and returns void. So now this magic function container, we built a container that can be constructed using any type func as long as the func implements the interface, that is, takes in an integer and returns void. So that's the beauty of this. Now this can be assigned, like the magic function container can be assigned a free function implementing such a signature, a lambda, or a functor. I want to pause for a minute and ask if there's any questions before I go on to the next slide.
Yeah, I just have one question. We didn't touch on the concept of a member function. Like, is std function not capable of handling member function pointers?
Yeah, so I deliberately did not touch on it because I think member functions get a bit more complex. So
Got it.
std function, I believe, is able to bind member functions as well, and like feel free to correct me if I'm wrong. But pointers to, I think it's non-trivial to store member functions. Either you have to bind them, or I'm not sure, to be honest.
Got it. Thank you.
I think member function should be usable with the std function. We can try this in parallel, but if you need to call a free function and a member function in the same way, I think you will need to just use the std invoke and pass the function and function pointer and the arguments to it. And of course, in the arguments, the first one ought to be the object on which you want to call this function.
At this point, got it.
Yeah. So that's a solved problem with the std invoke, but I think the function signature, if it matches this one, I think a member function should be callable. So I think we should just try it out and just check. Because I've not used it with a member function myself, but I know, it's just something that we should try.
Yeah, I haven't used it with a member function, as well, to be honest. I think it's usually not a good practice to pass member functions around.
Got it.
All right, I think 5 more seconds if anyone has any other questions. Let's move on.
I had one. So do we have a virtual function call overhead with this? I don't see virtual here. Oh, I'm sorry. There is a virtual in the concept. Yeah, sure.
Yeah, I'm going to touch on that as well briefly.
Yes, thanks.
Cool. I'll go to the next slide. So this magic function container now is able to is an interface, is a generic interface for any function that takes an integer and returns a void. But what's more interesting is like we're still not there at the std function, which is in which you can define your own arguments and the return type. And honestly, that's just some template magic around this. It's not. It seems a bit far from the code we have right now, but it's actually pretty close. So drum roll for some template magic. And this is what a std function looks like. So it's got a class function at the top, and which takes a template type name parameter t. It does not define it. Instead, the standard defines a specialization, which takes a return type and a variadic template for the arguments. I briefly touched upon previously that we can use C++20 constraints to make sure that the type, like the constructor does not accept just any type, but instead only accepts types which are invocable by the arguments and return the specific return type. So that is what the requires clause there is doing. And then it's simply at the bottom, you can see that instead of a raw pointer, I'm storing a unique pointer of the concept. The concept now itself is templated on the return type and arguments. It's fairly like straightforward to extend the previous concept to make it templated. The model is going to be templated as well. But it's the same idea. So if you see that it's a unique pointer, like it's a pointer to the concept, the mfunc is a pointer to the concept. And in the constructor, it's not really like mfunc is like on line 14. The function is actually assigned an object of type model instead of like a generic type concept. I've written here that it's not standard compliant. I was going to ask everyone, but I think we're a bit short on time. But the reason this implementation is not standard compliant, there's a couple of things, but the top reason is that because I'm using a std unique pointer for the ease of implementation, it makes this function only movable, not copyable. So the standard has two different types of functions. It has a move only function, which would look something like this, but it also has a copyable function. So the copyable function, this is not copyable. Hence, I've written that it's not standard compliant. So now if we take a step back and realize what we just done here, we started off with, okay, there's this std function type, which is generic, can be assigned various unrelated type. So essentially what we've now done is that we've taken various concrete types, like concrete unrelated types, like a free function, a lambda, a functor, and wrapped them into a single generic interface. And that is exactly what type erasure is. What type erasure does is that it enables you to use various concrete like unrelated types through a single generic interface. So essentially it's the term type erasure, you can guess, probably guess by this time, is that what it's doing is that it's erasing the type of these concrete types that you're trying to assign. And like it's achieving this type erasure using the technique that I just showed you and assigning it to a generic interface. So even in a strongly typed language like C++, you can have some smart techniques to hide away or like erase the types. So Ankur previously asked that, Ankur previously mentioned that, oh, there's a virtual, if you see the concept, there's a virtual function called overhead in a std function. So let's have a look at what the cost of a std function is. There's primarily two costs to using a std function. One is a heap allocation. Whenever the std function is constructed, like in my std function implementation, there was a unique pointer, so there's a new allocation there. So a heap allocation is done on construction. And second is a virtual function call, like indirect function calls, which are a bit more costlier than direct function calls in C++ or for any language in that matter. I've got a little asterisk on the first point of heap allocations because it is not completely true. So the standard does some optimizations, which is the like does a particular optimization called small buffer optimization, which is when your function signature is smaller than a specific size, it's not going to do a heap allocation. It's going to allocate that in like on stack in a byte storage. I'm not going to talk more about it in this presentation, but I've got a link at the end of the slides, and you can read more about small buffer optimization. It's quite interesting, actually. So just having a look at the requirements again. The first requirement was that this, like a type-erased container, should be able to hold unrelated types, sharing a common interface. Okay, seems like we've achieved that. And the second requirement, which I briefly touched on, was type safety. That is, it should be able to retain type information of the assigned object. I want to touch on type safety a bit now, talk about it a bit, and see why it is important in a type-erased component. And we'll move on from std function to std shared pointers and how a shared pointer implements type erasure in it to talk about type safety. So for the next couple of slides, I wanted to answer some questions. And I've got a base class, a noisy base, and a noisy derived class. Then each of those classes just outputs some stuff on construction and destruction. So when the base is constructed, it's going to call constructed base. On destruction, it's going to call destructed base. And similarly for the derived class. The derived class inherits from the base class. Okay, question one. So I've got a shared pointer to the derived shared pointer, which has the type noisy derived, like the template type name that I'm passing is the derived class. And the object type itself is the derived class as well. What do you think is going to be the output? And I'm going to be monitoring the chat next 30 seconds.
Sarthak, could you repeat the question for me again? I'm sorry.
Yeah. The question is that I've got a shared pointer, which takes the type derived. And the object that I'm assigning to it is also the object that is used to construct the pointer is also the derived object. So what's going to be the output of this code? And each of these, each of this output constructed and destructed phrases on construction and destruction. Okay, so Mr. K has set A. I'm gonna give it another, say, another 30 seconds. All right. Yeah, so A is in fact correct. What happens is that when I'm creating a derived class, like when this new derived, when the shared pointer itself is created, actually, like when the new derived is created, it first constructs the base class, then constructs the derived class, then this derived class is like the shared pointer points to this newly created pointer of the derived class. And on destruction of the shared pointer, the derived class is destructed first, and then the base class is destructed. So it is similar to how shared pointer is not really playing any special role here. This is the usual construction and destruction order in a inheritance hierarchy. Next question, 30 seconds again. Now I've got a shared pointer, in which the template type name that I'm passing is actually the base class, but the object is still of the derived class. So as opposed to the previous question, previous had derived class as the type and both the object type. But now I've got a shared pointer. So the pointer type is the base class, but it is pointing to an object of the derived class. What do you think the output is going to be? Okay, so Rock1 says A. Mr. K says A as well. Yeah, A is in fact correct. It's gonna do the right thing when a derived class is constructed. the base class should first be constructed, and then it should construct the derived class. And although the pointer type is base, like the pointer type is base, the shared pointer makes sure that destruction order is correct as well. So it destructs the derived class and then destructs the base class. Okay, now I've got a unique pointer instead of a shared pointer, and I've got a unique pointer in which the pointer type is the derived class, and the object type is also the derived class. What's going to be the output now? And I might have revealed the answer while going to and fro the slides. And keep in mind that there has to be a trick. Like if I'm asking some questions at some point, there has to be a trick. Okay, Mr. K says delay. Sorry, I'm unable to paste the class definition, but I can take a screenshot and paste. Maybe I can take a screenshot and paste it. But essentially, all it does is like see out stuff on construction and destruction. There we go. Okay. So when I've got a unique pointer of pointing to a pointer of type, like unique pointer in which the pointer type is derived, and it has also been constructed from an object type of derived, unique pointer actually does the right thing. It constructs the base, constructs derived, and then destructs them in the right order. Now I've got a unique pointer in which the pointer type is base, and the object that it is pointing to is of the derived class. It is very similar to how I had a shared pointer in this slide, in which the shared pointer, the pointer type was base. It was pointing to an object of type derived. But now the difference is that I've got a unique pointer. What's going to be the output now? Okay, so Raghavan says A. Another A is the favorite now. I should have shuffled the options, I think, to make sure people are not biased towards A. All right, I got a couple of A's. Yeah, I did mention that I'm asking questions, so it has to be a trick at some point, and I think most people fell for it. The trick. So when we're using unique pointer, in which the pointer type is the base class, but the object type is actually the derived class, it's not going to do the right thing. It's going to construct these correctly, but on destruction, it's just going to destruct the base. And this is extremely dangerous in actual code, because now, like when destructing, your base class, your derived class did not actually get destructed correctly. So you might have some resources in your derived class which you wanted to free up on destruction, and they never got freed. So this is quite dangerous, and this is the gotcha. So it seems like shared pointer with the same signature is doing the right thing, whereas unique pointer is doing the incorrect thing. And this is because shared pointer does some magic with type erasure, in which it actually uses the destructor of the object type instead of the pointer type. So when a shared pointer is destructed, each time it uses the deleter of the original object type instead of the actual pointer type. And we'll have a look at how that's implemented. And this is the importance of type erasure importance of type safety in type erasure. So it seems like if you look at unique pointers and shared pointers signature in the standard, On the left, I've got the unique pointer. It takes the type T, which is the pointer type. And it also takes the deleter type. And the default deleter type is the delete, the stood default delete, which simply does the delete expression for the type T. So this is what happened in the previous example. With unique pointer, what it actually did was it implicitly defaulted the deleter to be noisy basis deleter. And when you're using the basis deleter, it's only going to destruct the base. It's never going to destruct the derived class. Whereas in a shared pointer, you can see that the class declaration does not even have the deleter in there. So it's what shared pointer is doing is that while you're constructing it in the constructor, it takes in the object type, uses and stores the deleter of the object type using some type erasure magic, because again, shared pointer is a generic class, but you want to be able to store this deleter, which is a concrete type, in the class. But the deleter is not of the type. Like you simply cannot use deleter of type T. It's a whole different type. Like you want to store the deleter of the object's type as opposed to the pointer type. So you want to store that deleter in a generic manner. And that is where type erasure comes into play. And I think I'll just give it another 10 minutes, and we'll take questions. We'll see where we go from here. Okay. So shared pointer stores both template type information and the object type information, as opposed to unique pointer, which only stores the template type information. That's the takeaway from this. So let's start off with implementing a shared pointer. And I want to highlight particularly how shared pointer uses type erasure to implement this. So a very basic shared pointer will look something like this, where you're taking the type T. Type T is your pointer type, constructing the shared pointer from the type T. On destruction, it calls the deleter to the pointer, and you can see the members are a pointer of type T star and a reference count. Because this is a shared pointer, it needs to store a reference count. On copy, a shared pointer increments a reference count. On move, the reference count remains the same. It just moves the pointer. There's obviously I mean, if this were the real implementation, then like anyone could write the standard C++, I guess. But there's obviously a pretty big drawback with this implementation. I cannot do things like this. Well, actually, I can do this because my constructor is not explicit here. So I can, like, the pointer to the derived classes can be implicitly converted to the pointer of the base class. So the shared pointer will be constructed in this case, but on deletion, it's gonna call the deleter of the base class. So that's not right. So it still does not fill in the gap that I just discussed. So let's try to improve this implementation. As I mentioned previously, the gap is that shared pointer needs to be aware of the actual type that is passed during construction in order to delete it correctly. So let's look at an implementation. Yeah, so I think I've highlighted this previously. Shared pointer can store objects of any type T2 as long as T2, like the pointer to T2 is convertible to pointer to T1. A classic example of this is a derived pointer being converted to a base pointer. The interesting part is that it stores this type information of T2, like it has the type information of type T1 already available in the template, but somehow it needs to store the type information of type T2, and that is where it uses type erasure. It will call the correct destructor because it stores the type information of type T2, and unique pointer does not do this. Unique pointer only stores the type information of the pointer and not the actual object. So quickly having a look at what the classical implementation of shared pointers is. As I mentioned previously, shared pointer stores a pointer to the actual object type, and it also stores some control block information. The previous slide mentioned a reference count, so the control block will include things like a reference count, week count, and other data like custom deleters and allocators. The only thing we are concerned about here is the pointer to the object type T star and the custom deleter. So step one in building a shared pointer is that, okay, any type T2, I mentioned previously that any type T2 can be used to construct a shared pointer as long as a pointer to T2 is convertible to a pointer to T1. So the step one would again be something similar to building a stood function, wherein in stood function, if you remember, we had a constructor which could take any template, any type parameter. That is exactly the same in shared pointer. There's a constructor that can take any type Y as long as the pointer, like the pointer to Y is convertible to the pointer to T. And again, we can do this with C++20 constraints, something like this. You can see that I've added a requires constraint here that the Y star pointer is convertible to T star, created a shared pointer. And notice the interesting thing in the constructor on the top, now the shared pointer is calling another constructor, but the default deleter is to the type Y. So the difference between the unique pointer and the shared pointer is that unique pointer was defaulting the deleter to the type T, which was the template type parameter, that is the type of the pointer, and shared pointer is actually defaulting the deleter to the type of the actual object. So you can have a shared pointer of a base class pointing to derived A, derived B, derived C, and you can assign these shared pointers to each other, and they will still maintain the correct type information internally. So the challenge in the shared pointer, like the tricky part in the shared pointer now becomes, how do you store this type information of the type Y and the type deleter? And I've touched upon this previously. It's really the exact same thing we did with a stood function. In a stood function, we had a type func which we wanted to store generically, and there was some common interface. In a shared pointer, we have two concrete types, the type Y and the type deleter, and we want to store these with a generic interface. So we want to erase these types from the shared pointer structure itself. This is exactly the thing I mentioned. So yeah, skipping straight to the implementation. You can see that on the right, I've got a control block base, which has got a virtual destructor. It stores a ref count, which is similar to the previous one, initializes it to 1. And then this control block base is again a base class. Then I've got a derived class, which takes in these two concrete types, the object type and the deleter, stores the pointer to the object type, stores the deleter, and it's got a virtual destructor override. And here it actually, like the deleter is the actual deleter to the object type, not the pointer type. On the left, you can see that all the shared pointer is doing now is like the exact same thing that a stood function was doing. It's storing a pointer to type T, which was my base pointer, like in an example where I had a base class and a derived class. The shared pointer class is storing a pointer to the base class, but then it's creating a control block object, which type erases these two concrete types, the object type and the deleter type, and storing it in a generic fashion with a control block base class. So that's the interesting thing that a shared pointer is doing. It's like completely type erasing the type of the concrete, type of the concrete object type and the deleter associated with it. So now what you can do is that you can have like a shared pointer of a base class and like assign it to multiple derived class. And I hope I've got an example of that here. Yeah, so this slide basically highlights that it's very similar to stood function. And this is the example that I've got. So now I've got two shared pointers, which are pointing to the same base class, which are pointers of the same base class, but they're assigned to different derived classes, which derive from the same base. and sp1 equals like assigning any of the shared pointers to each other is completely valid. When sp2 is destructed, it's gonna call the correct destructors. It's gonna like destruct derived 2 and then the base class. And when sp1 is destructed, it's gonna destruct derived 1 and then destruct the base class. Yeah, so that's how shared pointer type erases the concrete object type and the deleter. And that's the very reason why unique pointer failed with one of the examples that I showed, but shared pointer actually did the right thing. Yeah, I think I'm gonna stop here. There's a very neat technique with shared pointers using shared pointer void, which is like a modern version of void star. You can assign basically anything to a shared pointer void. You can assign completely unrelated types to a shared pointer of void, and it would do the correct behavior. For example, like on the top code in the slide is not going to compile. You cannot have a unique pointer of type void because you cannot have a deleter to a void star pointer. But the code at the bottom, these noisy foo and noisy bar, like consider them to be completely unrelated types. This is completely valid code. When each of these classes get destructed, it's like the correct destructors are going to be called. And that's the beauty of type erasure inside shared pointer. The C++ standard says that an object cannot be deleted using a pointer of type void star because void is not an object type. But shared pointer is able to get around this limitation and achieve correct and defined behavior in a generic fashion. Yeah, I think I'm gonna skip Studeni for today. Can take it up in one of the next sessions, and I'm gonna take any questions if anyone has any questions.
Yeah, okay, there's not a question as such, but I'm just going to guess it here. If std shared pointer void can point to anything, I believe std any can just be a composite of std shared pointer if heap is allowed, right?
Yes, I think that's a very interesting question. And had I covered Studeni, that was one of the first questions I was going to ask. So I guess I'll ask you this question. So if you assume that Studeni does do a heap allocation, which, like, spoiler alert, it does do a heap allocation, what do you think would be a difference between Studeni and stud shared pointer? And I guess another hint to that would be Studeni. One of the requirements of Studeni is that the type should be copy constructible. Like, this is not a quiz. I'm just trying to
make you think.
Not answer the question.
Yeah, that's a valid point. I mean, if there is no difference between the composite type and the original type containing it, why the original type would be the real question.
So what do you think happens when you copy a shared pointer?
It would definitely increment the ref count. So that's one thing that's going to happen.
And what would happen when you copy a stud any object?
Oh, std any is unique ownership, I see.
So stud any actually gives you value semantics. That is, when you copy a stud any object, it's going to actually, although stud any internally does store a pointer, does do heap allocations, but on copy, it's going to copy the actual object. Whereas stud shared pointer on copy is just going to increment the ref count. So all those, like, on a high level, it seems like stud shared pointer of void does achieve the same behavior as stud any. The main difference is that stud any has value semantics, so you can pass it similar to like any primitive type value you would pass, whereas shared pointer does not have those value semantics.
Got it. The distinction factor being that copy is not a cheap copy, it's actually the copy of the contained type that is being erased.
Well, there's obviously a cost, but a lot of times you do want to copy,
The
like you do
underlying
want a
type.
true copy as opposed to the ref
Yeah, got it.
increment. But that's a great question. Thank you for bringing it up.